Okay, let's do the next example. Alright, so we're going to show that the integral from 0 to infinity ln of x, log, this is log x, natural log, over 1 plus x squared dx is equal to 0, the natural log. Okay, so how do we do that? We are going to, first we're going to see what closed curve we choose. We actually will choose this curve. We're going to choose this curve, the curve we used. So the upper semicircle with radius r, and then use the interval from negative r to positive r along the real axis, and we use a counterclockwise orientation. All right, so that's the big picture we're going to see. And back to this concrete problem, we have a small issue, not too big. First, x cannot be 0, so we have to remove this small 0. We have to remove 0. How do we remove 0? We use another smaller upper semicircle to exclude 0. Right? The other thing is that when we use the analytic function, we will possibly use f of z is equal to natural log of z over 1 plus z squared. So we're going to use this function. But for this function, remember, for the Euro purpose, we will cut along the negative x-axis. So this part is undefined. This piece is undefined for the natural selection of a branch for the natural log. So in order to make, I do want this part, right? So what do? We're going to cut the complex plane not along the negative x-axis. We're going to cut the complex plane along the negative imaginary axis, right? So that's two things. One thing, we need a small circle to exclude 0. And second thing, we want to use this negative real axis, so we cut the complex plane along the negative y-axis. All right, so first define G be z in C. Z is not equal to 0, and the argument of z is between negative pi over 2 to 3 pi over 2. So this way, right? From this negative part to the 3 pi over 2. So this is our domain for the natural log of z. All right, so if we have z equal to modulus of z times ei theta, here theta should be between negative pi over 2 and 3 pi over 2. Then our complex logarithmic function becomes the Euro logarithmic function, this is real logarithmic function, plus I theta, this is our setting, right? And let 0 less than little r less than capital R, and let gamma be the closed curve in the above, not in the stuff above. So what is a closed curve? Closed curve means you use the small upper semicircle and the big upper semicircle, and then use clockwise, counterclockwise orientation. Counterclockwise orientation. All right, then let's see. Along the interval r and capital R, this log z is just a log absolute value of z, because the argument is 0, and which is log x. And along negative capital R and negative R, the complex logarithmic function is log absolute value of the modulus of z plus, what is this? This is pi. Argument is pi, so it's a pi I. So it's a log. Here, this time the x is negative, so it's a log negative x plus pi I along this this piece. All right, then let's see. We have the integral f of z. F of z is okay. F of z is log z over 1 plus z squared. Along gamma dz is equal to the sum of 4 parts. So from little r to capital R, log x over 1 plus x squared dx. And plus IR, well, you will see what is IR. IR comes from the dx, okay? So let's check it. So from 0 to pi, well, let's gamma capital R. Let's this is gamma capital R, gamma little r. Let's slow down. It's a log of z over 1 plus z squared dz, plus from negative capital R to negative r, log z. Log z becomes a log absolute value of z plus pi I and 1 over z squared dz, right? And then the clockwise, and the plus integral along gamma little r log of z 1 plus z squared dz. All right. Now let's do it. First one we just copy it. And second one here, z is capital R E I theta. So dz is I R E I theta d theta. So that's why I wrote IR first. So it's plus IR, this coefficient is from 0 to pi. You'd go counterclockwise orientation, and the log, it becomes a log R plus I theta over 1 plus r squared e2I theta and ei theta d theta. Right? And second one, it's from negative r to positive r. This is log negative x plus pi I 1 plus x squared dx. Z is just x, but z in this time is a negative, so when you get absolute value, it's negative x. Okay, and this one is similar. Just change the capital R to be the little r. So plus I little r integral, but it's from pi to 0. From pi to 0, log little r plus I theta and 1 plus little r squared e2I theta, ei theta, and d theta. All right, so you have 4 parts. And what's next? The next, we're going to see that this function has just one simple pole enclosed by this curve I, right? Z equal to I is the unique simple pole enclosed by gamma. Unique simple pole enclosed by gamma. So we're going to compute the residue of F with respect to I. The residue of F with respect to I. All right, so it is actually equal to the evaluation. First, you evaluate the numerator at I. Second, you will get I minus negative I. Check here, so natural log of z squared minus negative 1. So it's a natural log of z minus I, z plus I. And then you're going to multiply this by z minus I. We're talking about the simple pole evaluation for the residue. And then you just cancel the z minus I, then you can substitute z by I, so you get this. Log I has modulus 1. I has modulus 1, so log 1 is 0. I has a argument pi over 2, so it's a pi over 2I. That's log I, and here denominator is 2I. I minus negative I is 2I. And cancel that, you will get the residue is pi over 4. Okay, the residue is pi over 4. And once we get this unique residue, this integral, remember, in the formula, it is this average of the integral is equal to the residue. So we get the integral is equal to what? So pi squared I over 2. Pi squared I over 2. All right, so this is the evaluation for the contour integral. Now we are going to place this pi squared I over 2 in the formula. In this formula, what will we have? We're going to keep this term and this term in one side. All right, so let's check what we have. We are going to keep these two in one side. So let's check what is the sum of them. No, sorry, not this one. This one, the first and the third. Okay, plus pi I. Plus pi. So here you're going to, of course, you will use u substitution. Let negative x be u. Then you will have little r log u over 1 plus u squared, and then negative du, and plus r negative r pi I 1 plus u squared negative du. And negative sign will be used to flip this limits. So you will get here and here they are same. So twice from r to capital R log x over 1 plus x squared dx. And this one is integral from little r to capital R pi I du over 1 plus u squared. Du plus 1 plus u squared. Okay, now remember that we will let little r approach 0, capital R approach infinity. So this integral, remember it has antiderivative arctangent of u. So this integral will approach pi over 2. R approaches 0, capital R approaches infinity. This limit of the integral will approach pi over 2 times pi I. So it will approach 2 integral r, capital R, log x 1 plus x squared dx plus pi I times pi over 2 is a pi squared I over 2. All right? Okay, excellent. So this tells us if r approaches 0 and capital R approaches infinity, our right-hand side, those two terms adding together, we will have 0 infinity twice, log x over 1 plus x squared dx, and plus limit capital R approaches infinity, integral this one, 0 pi I capital R log R plus I theta ei theta over 1 plus r squared e2i theta d theta. This is a second term and third term. Little r approaches 0. It's from pi to 0. Here, I little r log little r plus I theta ei theta 1 plus r squared e2i theta d theta. And remember, we have this term plus pi squared I over 2 is equal to, this whole sum is the integral. It is equal to pi squared I over 2. Or what does it mean? You cancel them, it means this twice of the integral is equal to the negative of the limit. The negative of the limit. Right? So, well, that's good. Now let's try to show both limits are 0, then this one has to be 0. Okay, so next we show that both limits are 0. Both limits are 0. Okay, so now let's check. We're going to compute the ops value. So modulus, I'm not using r, I'm using the a general letter, rho, from 0 to pi, log rho plus I theta 1 plus rho squared e2i theta ei theta d theta. All right, so we're going to put this into the integral. Once we put it into integral, ei theta has modulus 1, so you don't see it. And this part, if you put it into it, you will have rho, log rho plus I theta modulus over 1 plus rho squared e2i theta modulus d theta. Right? You have this. And remember that 1 plus rho squared e2i theta modulus is in the denominator. We need it to be greater than or equal to rho squared minus 1. Right? We need to be greater than rho squared minus 1. When you put the flip it, it will be less than. Okay? It will be less than. All right, so this is obvious. You check that. This is always correct. Okay. And this one, we're going to use the triangle inequality. So this is less than or equal to the integral 0 pi. The first one, it is rho, log rho. Here it's a modulus rho squared minus 1d theta. And the second part is what? Is 0 pi rho modulus theta. Theta is also positive. Theta is between 0 and pi. It's positive. So rho square minus 1. What else? D theta. Yes, d theta. So you integrated. This one is constant, so it's equal to rho of value log rho square minus 1 times pi. This one, you integrate theta, you get 1/2 theta squared. So it's a rho over modulus rho square minus 1 times pi squared over 2. By the way, this one, I said it's obvious. Why? Because so first you get a 1 here. You get a 1 here. This quantity, if you write it, it can be written as a distance between this point and the -1. This point and -1, if it's inside, the closest point will be this point. The closest distance will be here. If it's outside, it will be here. But either way, it is always a rho square minus 1. It's always a positive axis, positive one. So anyway, I mentioned it's too fast, I feel. All right, then let's see. If rho approaches 0, if rho approaches 0, then check here. This one actually has a limit of 0. Rho times the natural log of rho has limit of 0 when rho approaches 0. Even though natural log of rho approaches -infinity when rho approaches 0, but it grows slower. All right? So, and when rho approaches infinity, the denominator has a bigger power. The denominator has a bigger power, so it also approaches 0. Both approach 0. So we get the twice of integral 0 infinity natural log of x over 1 plus x squared dx is equal to 0. You cancel 2, you have the answer. All right, so this is the complete computation, And this computation, the whole thing is not difficult, but there's one thing I want to mention. So usually this is a very interesting selection when you have 0 infinity or -infinity to positive infinity integrals. But when you have this like a very successful model, you need to modify it a little bit when you have special functions. When you have natural log, you need to use a little arc to exclude 0. When you have natural log, you have to modify your your cutting line, your branch, your selection of the branch. So that's the thing I want to mention. Besides this residue theorem application, actually this problem itself is not that horrible. It's not really horrible. So the thing is the following. Let's see. There's a discussion about this integral online, and let's see how we solve it by the real analysis, not the real analysis, the regular analysis. All right, so we first write it as 2 pieces. Actually, this one itself is already the combination of 2 types of improper integral. Remember, 2 types of improper integral. Type 1, the domain is infinite. This domain is infinite. Type 2, at the endpoint, you get infinity. So this is type 1 plus type 2 improper integral. And let's check here. For example, this one, 0, 1, natural log of x 1 plus x squared dx. We're going to let x be 1 over t. If x is 1 over t, then dx is negative 1 over t squared dt, right? And when x is 1, t is 1. When x is 0, t actually corresponds to infinity. And the natural log of x becomes negative log t. 1 plus 1 over t squared. And here you have negative 1 over t squared dt. That's a dx. Cancel negative negative sign. This d squared multiplied by 1 plus 1 over t squared. Remember, this negative sign, they are cancelled. Right? You see it? So you actually get this. But this one is not the, infinity. But this one is not this one. They are opposite. They have opposite sign because they have different upper and lower bound. So the sum is 0. So the sum is equal to 0. So it looks very fast, right? It looks very, very fast. And whenever you have such 0 infinity and you have x squared or log x, possibly this trick x equal to 1 over x is helpful. It's helpful. Another thing I followed from this trick x equal to 1 over x. Let's check another thing. It's like this. Let's compute what is from the integral from 0 to infinity dx over 1 plus x squared 1 plus x to rth power plus x to rth power. Okay, well, let's see what we can do for this. We're going to break it into two pieces. One is from 0 to 1. We just copy it. 1 plus x squared, 1 plus x to rth power, and the other one is from 1 to infinity, dx over 1 plus x squared, 1 plus x to rth power. All right? And for this term, I'm going to apply this trick. Let's see what we have. Here I'm going to use this trick. Let's see, this integral becomes from infinity to 1. Dx is 1 over t squared dt, negative 1 over t squared dt. Denominator, 1 plus 1 over t squared, 1 plus 1 over t to rth power, and plus the second term. Right? And then we're going to multiply two sides by t squared, top and bottom by t squared. So this t squared canceled. You get 1 plus t squared. And then we'll multiply by, okay, t to r. So it's negative t to r's power dt. Remember the first thing, we'll multiply top and bottom by t squared. It becomes t squared plus 1. Here it becomes a t to r plus 1. And numerator you have a t to r dt, and plus integral 1 infinity dx 1 plus x squared 1 plus x to rth power. Right? And then this negative sign flip with a infinity 1. So you have 1 infinity x to r's power dx. I'm going to use x instead of t. 1 plus x squared 1 plus x to rth power, integral 1 infinity dx 1 plus x squared 1 plus x to rth power. Well, you just add in the ground. You add in the ground, you get a 1 plus x to rth power 1 plus x squared times 1 plus x to rth power dx. So you cancel them, you see what? You see this function. You see it. What's this? This is pi over 4. Remember, 1 over 1 plus x squared has antiderivative arctangent. At infinity, it's a pi over 2. At 1, it's pi over 4. So the subtraction is pi over 4. So this function, it actually does not depend on r. You see here, r disappears. There's no r. So this is a very interesting integration. Right? So this trick is very, very useful and successful, and sometimes when you have such examples. Right? So another one, we don't finish it. So let's check what happens if we have the same problem, not same, this problem from 0 to infinity. What do we have? Log x 1 plus x squared dx. Let's see. We just let u be log x. Then du is 1 over x dx, right? Du is 1 over x dx. And the domain 0 infinity becomes negative infinity to positive infinity. All right, let's check. Let's check. Let's check what we have. We have negative infinity to positive infinity. This is a u. And here you get what? Dx is x du. Okay, so it's x du. I'm not finished. So 1 plus x squared. X, what is x? X is e to u. So this is actually e to u. U e to u du over 1 plus e to 2u. And then we move this denominator down. We not move. We divide numerator and denominator by e to u. So we get integral negative infinity to positive infinity. U du. 1 over e to u is e to negative u. E to 2u over e to u is e to u. It's like this one. All right, so we use substitution u equal to natural log of x. We directly have this. And then we can directly conclude this is equal to 0 because this function u over e to negative u plus e to positive u is an odd function. The integral of odd function over symmetric domain is always 0. Okay? Of course, we need to guarantee this is it is a convergent improper integral. It's convergent improper integral. Okay. Next, let's see another attempt to solve it. Another attempt to solve it. This one is similar. It's quite similar to this. It's from 0 to infinity, natural log of x 1 plus x squared dx. This time I do not use substitution u equal to log x. I will directly choose u. We will let x be. Let me see. Okay. but possibly that's not that interesting. Let's do this computation. We're not using 1, we're using a square. We're using a square. Let's check this one. This is very fascinating. So we will let x be a tangent theta. It's crazy. X is a times tangent theta. Then what is dx? Dx is a secant theta squared d theta. Right? Secant theta squared d theta. So this integral is theta is 0. At infinity, theta is pi over 2. And natural log a tangent theta over a square plus a square tangent theta squared and times a secant theta squared d theta. Actually, this is the similar trick when we try to find the antiderivative of 1 over 1 plus x squared. Right? So here's the dx. Dx is this. And if you factor out a squared, if you factor out a squared, you will get 1 plus tangent theta squared. And 1 plus tangent theta squared is just secant theta squared. You cancel them. And a squared, you cancel 1 copy. So it becomes 1 over a integral 0 pi over 2 natural log of a tangent theta. Right? D theta. Okay. So now let's check this one. It is equal to, natural log has a multiplication rule. So it's 1 over a natural log, 1 over a integral 0 pi over 2 natural log of a d theta and plus 1 over a integral 0 pi over 2 natural log of tangent theta d theta. Right? And this one, this is constant and natural log of a times pi over 2. So it's a pi natural log a over 2a. That's the first one. And the second one, tangent, we can write it sine over cosine. So this becomes sine theta minus 1 over a natural log of 0 pi over 2 natural log cosine of theta. Remember, we're talking about the first quadrant. All the trigonometric functions are positive, so it makes sense. All right, and what else? Here, we're going to cosine. Cosine is sine pi over 2 minus theta. So we let u be pi over 2 minus theta. So natural log sine theta d theta minus 1 over a, it becomes pi over 2 to 0. Remember, we use pi over 2 minus theta. So it's from pi over 2 to 0. Natural log sine over u d theta becomes a negative du. And this negative sign can cancelled with a flip of a top and bottom, and then you will get subtraction. This part, it becomes minus. When you flip it, you create a negative sign, cancel with this negative sign. So 0 pi over 2 natural log of sine u du. So this is 0, right? So the final answer will be pi log a over 2a. This process is almost identical to the antiderivative of 1 over 1 plus x squared. But you have to handle this natural log of a tangent of x. Natural log of tangent of x. And this is a general formula because when a is a 1, it's a 0. When a is not a 1, you will have other different quantities. Correct? Okay, excellent. So, yeah. So sometimes when we have one problem, we may think about different way to solve it, and then we will compare the process. That is a very interesting process. Okay, thank you very much. And we finish this example. We will do another example.